Hey folks, in this video I'm going to prove a couple of the derivative rules that we showed in the other videos. This is not going to be a required video by any means. It's one of my favorite proofs is of the power rule. Someone asked me the other day, do you say that for every single proof that you do? And I probably do. I enjoy proofs quite a bit. So if you are just looking to use the rules and get yourself through calculus, and this may not be the video for you, but if you are curious about how these are proved, then please by all means watch on, and let's take a look at how the power and product rule are proven. So some of the vocab we're going to have here: limit, derivative, pretty standard stuff we've been talking about. Binomial theorem is something that you may have heard of before. If you know the binomial theorem, you're going to be able to skip kind of the next two slides because I'm going to kind of do an intro to that. The product quotient we're actually not going to look at. Prime, f prime, just remember of x, derivative, and then higher order derivative we're actually not going to talk about either. But this is an old slide, so sorry I had this on here already. So let's take a look. So a little combinatorics introduction. So if you didn't take FST, then you may not have had any introduction on combinatorics at all. Combinatorics is a branch of mathematics that has to do with counting things. It's one of my favorite branches of math. That's true. You can actually believe that one, as opposed to like my favorite proof. But it's a way to count things or to find the number of combinations that something could happen. So like if you have 3 people running in a race, so 3 runners, and you're asked how many ways can those 3 people finish? Well, it could be A, B, C, B, A, C, C, A, B, and I'm not trying to order these in any specific order or anything. I guess A, C, B, B, C, A, or C, B, A. So there are 6 different ways that could happen. And there's a smarter way to do that, to count these as opposed to writing them out, because what if you had like 15 runners, right? Writing them all out would take forever. So those 3 runners, the way I think about it is there's 3 spots to fill. There are 3 options for the first one, A, B, or C. For each of those, 2 people could finish second, and then the third place person is fixed. You multiply them together, 3 times 2 times 1 is 6. 15, same deal, 15 times 14 times 13, all the way down until 2 and 1. There's a special symbol for this. It's called 15 factorial. Use an exclamation point. I always think it's exciting because it has an exclamation point on it, but that's how you order n things. So if you have n things and you want them ordered, you do n factorial. Now, this gets a little bit more interesting. If you have 15 people and you're only going to have like a first, second, third, you can just do 15 times 14 times 13, right? So 15 times 14 times 13 would give you the first, second, and third place, and the rest of them I don't care about, right? Or maybe you have like a president, a vice president, and a treasurer that you want to pick. You could do 15 times 14 times 13. This is called a permutation. So that would be 15p3. So you're picking 3 things out of 15. And to do that, the way the formula works is you do 15 factorial, which is 15 times 14 times 13 times 12, all the way down to 1. And then you divide out, well, what don't I want? I don't want 12 down. So you divide out 12 factorial. And you get that by doing 15 minus 3. In general, NPR is n factorial, excuse me, not 15, n factorial, divided by n minus r factorial. So that's how you pick things where order matters, right? You care who's first place, you care who's second place, you care who's third place. What's really going to be interesting for us is what's called a combination. So a combination, similar idea, but instead of caring about the order, I'm not going to care about the order. So in this case, it might be like you have 15 people. Apparently 15 is my number today. And you want a committee. Committee. Okay, so a committee of, let's say, 3 people. Well, a committee, the order doesn't matter in which they're picked. Right, you're just going to have like a group. I think about like you have your 15 people, and there's going to be a group of 3 people, right? And those 3 people are like equal in power. They don't have like roles. So in that case, I am going to pick the 3, but it doesn't matter what order I pick them. So I have to get rid of the number of ways to order them. There are 6 ways we know to order 3 things, so you have to divide by another 6. So in this case, it would be 15 factorial over 15 minus 12 factorial, or 15 minus 3 factorial, so we have 12 factorial. But then I'm going to divide out another 6, which is 3 factorial. This is be 15 choose 3. Another way that you saw that written sometimes is just 15 over 3 in parentheses like this. And that is the number of ways to pick 3 things from 15 where the order doesn't matter. In general, n choose r is just n factorial over n minus r factorial times r factorial. So it's just NPR, and then you divide out the number of ways to order those R things. Okay, so this is a really, really quick introduction to combinatorics, but this is really the only thing we're going to need. This is the number of ways to pick R things from n total items, where the order doesn't matter. So let's see how that's going to come into play with what's called the binomial theorem. Binomial theorem has to do with expanding binomials. So a binomial is something with two terms. So like x plus y squared. X plus y is a binomial, 1, 2 terms. X plus y squared, we know how to do that. X plus y, x plus y. If you're one of those people who likes to make a box, you can make a box, whatever. X squared plus xy again, out and inside terms, and then last terms give me y squared. So that is x squared plus 2xy plus y squared. Notice the x starts with a degree of 2, then it's a degree of 1, and there's no x left at all. The y climbs. No degree at all, then 1, then 2. Let's do x plus y cubed. So that'd be x plus y, x plus y, x plus y. Well, I already have this, right? This is x squared plus 2xy plus y squared. X squared plus 2xy plus y squared. Now let's multiply by the last one. So x times x squared is x cubed. X times 2xy is 2x squared y. X times y squared is xy squared. Y times x squared, we have yx squared. And then we have a 2xy squared. Xy squared. And then we have y times y squared is y cubed. Simplify that. We get x cubed. Let's see, that's x squared y, we have 2, and then one more right here. So those we're using right now. So we use the x cubed. So we have 3x squared y. Those are gone. Let's get xy squared. Looks like we have 3 of those as well. So 3xy squared, and then we have a y cubed. Okay, so we have our squaring, we have our cubing. Let's look at the fourth. So x plus y to the fourth. This is the last one I'm going to do. So x plus y to the fourth would be x plus y 4 times. Times x plus y times x plus y. Another way to think about that is it's x plus y squared twice. So it's this thing multiplied by itself. So x squared plus 2xy plus y squared times x squared plus 2xy plus y squared. If you want to multiply this out on your own, you can. But I'm getting to what is going to be a general pattern here. This is going to be x to the fourth. But notice once again the x kind of goes down in power, the y kind of goes up in power. So x to the fourth, and it's going to be plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus, what do we have, y to the fourth. Okay. So this actually follows what is called the binomial theorem. And the reason I talked about combinatorics first is because when you're looking at this, you're thinking about the number of ways to pick the number of terms that are going to mean each one of these. So let's look at like x to the fourth. There's only one way to get x to the fourth. You need this x, you need this x, you need this x, and you need this x. Right? That's the only way to get x to the fourth. X cubed y, though, x cubed y, basically from each one of these terms, I can pick either x or y. So like x cubed y I could get by getting this x, this y, and this x. But that's not the only way to do that. How many ways are there to do that? Well, I'm going to pick the y from any one of the 4. There are 4 ways to do that. How many ways to take 2 x's and 2 y's? Well, I could take the x from the first 2 and the y from the second 2. Or I could take xy, xy. I could take xy, yx. I could go yx, xy, yx, yx. If you count all the ways, there's going to be a total of 6. And really what I'm doing here is from 4 things, I'm picking 2. From 4 things, I'm picking 2. In this case, from 4 things, I was picking 1 to be a y. This is just the number of ways to pick 4 things. Well, the way that it usually works is 0. So I'm picking 0 y's from 4 things, x to the fourth. Then I'm picking 1 of those y's, and that's x cubed y. And then I'm picking 2 y's, x squared, y squared. And then I'm picking, let's see, this is 3 y's, xy cubed. And then I'm picking all 4 y's. So there's only one way to do that. I pick y, 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 y. Y to the fourth. So what's happening here is I'm just using combinatorics to do this. And this is what binomial theorem is. So binomial theorem, whoop, too far. Binomial theorem says that x plus y to the nth power, so whatever n is just, it's going to be n choose 0, x to the n, and then n choose 1, x to the n minus 1 y. And then n choose 2, x to the n minus 2y squared. Notice the n is coming down, right? The x exponent is coming down. The y exponent starts at 0, technically, right? This is y to the 0. Then y to the first, y to the second, y to the third. And you keep going with that until you get to n, choose n. That's the last one, so you're only picking y's, y to the nth power. And then it'd be x to the 0, technically, right? Because there's no x's left. This is binomial theorem. And this is going to be what our proof is going to hinge on. And something I can't go into, but the Pascal's triangle, which we have hanging in our room, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Next one's 1, 4, 6, 4, 1. Then 1, 5, 10, 10, 5, 1. What you notice is these are actually all of the ways to find the number of combinations. You get each value by adding the 2 above it, right? 5 came from 4 and 1, 10 came from 6 and 4. And these are going to be the coefficients for each one. Notice we have 1, 2, 1 up here, then 1, 3, 3, 1, 1, 4, 6, 4, 1. They're just the rows of the triangle. Very cool. The next one will be 1, 5, 10, 10, 5, 1. And so the nth row is going to be the coefficients for your x plus y to the nth power. Cool. All right, let's see if we can actually get into some calculus now. So our rule was the derivative of x to the n is n times x to the n minus 1. So the question is, why? Why? And what's interesting is the way people remember this, they always think the n comes to the front, and then this reduces 1. That really has nothing to do with how the proof works. Let me show you. So let's think about this from definition of derivative, the limit definition of derivative. Remember, f prime of x is equal to the limit as h approaches 0, f of x plus h, minus f of x, divided by h. Okay, so let's do that with this function. So with this function, it's going to be the limit as h approaches 0. F of x plus h would be x plus h to the nth power minus f of x divided by h. Okay, or sorry, f of x is x to the nth. So we just did this expansion using binomial theorem. All of that 10 minutes I spent talking to you about combinatorics and binomial theorem are what was leading up to this. So this is the limit as h approaches 0 of x to the n plus, so that was n choose 0, and then n choose 1, x to the n h, and then n choose 2, x to the n minus 1, sorry, this is n minus 1, this is n minus 2, h squared, and that's going to keep going, and then we're eventually going to have a n choose n, h to the nth power. And then we subtract off our x to the n, and we divide by h. Okay, so this is our binomial theorem for that expansion of x plus h to the n. Let's look at Pascal's triangle a little bit closer. I'm going to go up to 5 again. 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. We'll go to 6 this time. 1, 6, 15, 20, 15, 6, 1. So, one thing to notice. N choose 0 is always 1. There's only one way to choose nobody. You choose nobody, right? There's not an option, okay? So this is limit as h approaches 0. N choose 0 is just 1. So this is going to be x to the n. Now let's look at n choose 1. What do you notice about all of these numbers? It's just n, right? This is the first row, second row, third row, fourth row, fifth row, sixth row. So if you're choosing from 4 things, the number of ways to choose one of them, well, you have 4 options. Right, the number of ways to choose from 5 things, you have 5 options. So this is just going to be n, always. The nth row just gives you the number n. So n x to the n minus 1 times h. Now n choose 2 is harder, right? N choose 2, we start to have weirder numbers, right? 6 is in the 4th row, 10 is in the 5th row. I don't know what that is, so I'm just going to leave it as n choose 2, x to the n minus 2h squared. And then we go all the way to n choose n, h to the nth power. It's an h. Minus x to the n over h. My n's are starting to look like h's, sorry. Okay, now look, the x to the n's cancel. You may have noticed that with every polynomial that we use, that first term always just goes away, right? So that's gone. And so we have limit as h approaches 0. And now what you always notice is after that x to the n is gone, you have an h left in every term. So let's factor that out to the front. So we have h, now we have n x to the n minus 1, plus n choose 2, x to the n minus 2, h. That's going to keep going until we have n choose n, h to the n. That's all divided by h. So we canceled against that h, thank goodness. And now notice what we have left on the top. Every term has an h in it except which one? This guy right here. So if h is approaching 0, all of these cancel. All of them go away, and I'm left with nx to the n minus 1. I love that proof. That is so cool. So the way to think about this is like, what happened is the first term just has an x, so it goes away with the last one. The next term has one h, the next term has two h's, the next term has three h's. When we factor out that h, this is like the Goldilocks term, right? All of these have too much. This one doesn't have enough, so it's gone. All of these are gone because h is going to 0, so even though I pulled the h out, those all canceled. This is the Goldilocks term that has exactly one h. It's the only one that has exactly one h, so when you pull it out, it's gone, it cancels, and you're left with nx to the n minus 1. What a cool way to integrate combinatorics with calculus. I love that. Very cool. So there is our proof. End proofs with a line, proof square, maybe a QED. Great way to end a proof. Awesome. So the product and quotient rules are other ones that I kind of waved my hands in the other video and said, you know, we are just going to assume that this is right, right? For this one, we had a trick. It was Foggy-Goffey, F-O-G-I, Foggy-Goffey. And this guy down here was low D high minus high D low over the square of low E go. So fancy little terms for these ways to remember these, but we don't really have a proof yet. So we're going to prove number 5. The proof for number 6 is very similar to the proof for number 5, so I'm not going to do it. If you want to try it on your own, you can. If you do try it on your own, I would encourage you to think about it this way. F of x multiplied by 1 over g of x. Because now you really have a product of two functions, and that will get you into using product rule. But similar proof, I'll just show you how the quotient or the product rule works. So we're trying to find the derivative of f of x times g of x. So as always, we'll go back to limits. Limit as h approaches 0, f of x plus h, g of x plus h, minus f of x g of x, all divided by h. So looking at this right now, it sure doesn't look like what we want. To find this, remember, f of x will be just by itself. G prime of x will be g of x plus h minus g of x over h, right? So we kind of have some of the pieces in here, but it's looking like we don't quite have what we want. So what I'm going to do here is I'm going to use a little trick. I'm going to add and subtract the same thing. What we're going to add and subtract is f of x plus h, g of x. So we're going to add and subtract this from our little difference quotient here, and we're going to see what happens. I'm not going to do it on the top. And adding and subtracting something just makes 0, so it doesn't really do anything. So we have limit as h approaches 0, f of x plus h, g of x plus h. I'm going to put this right in the middle. So I'm going to add f of x plus h, g of x, and I'm going to subtract it, f of x plus h, g of x. So I've just essentially added 0. Right, because I added and subtracted. That doesn't do anything. Minus f of x g of x, all divided by h. Now what I'm going to do is I'm going to factor certain pieces out where I want them. I'm going to factor certain pieces out where I want them. So what I'm going to do is I'm actually going to take this piece, and I'm going to use it over in the front here. So I'm actually going to switch the order. In fact, to do that, I'm just going to do this. I'm going to subtract and add instead, because that's just going to make my life a little easier. So instead of adding and subtracting, subtract and add doesn't change anything. So let's look at these first two things. What do they share in common? Well, they share f of x plus h. So we have limit as h approaches 0. F of x plus h. I'm going to pull that all the way out to the front. In fact, I'm even going to pull it off of the fraction. So then I'm left with g of x plus h minus g of x divided by h. I'm doing a lot of things at once here, so I'm splitting up the fraction, and I'm also pulling some stuff off. So then I have plus limit as h approaches 0. I'm going to do the same thing over here. What do these share in common? Well, they share a g of x. So I have g of x multiplied by f of x plus h minus f of x divided by h. And you can kind of see where this is going, right? I mean, this right here is the derivative of f of x. Because there's no h here, g of x is a constant. So this is g of x multiplied by limit as h approaches 0, f of x plus h minus f of x divided by h. And over here, f of x plus h is not a constant, but h is approaching 0. And there's no danger in plugging in h right here, right? If I plug in 0, it's not going to give me a 0 over 0 or an undefined or anything like that. So this is just f of x. So I'm going to pull out an f of x. and multiply by the limit as h approaches 0, g of x plus h minus g of x over h. Well, what do we have? This is f of x times g prime of x. Plus, over here, we have g of x times f prime of x. And there is our foggy Goffy. It's even in the right order. I was worried it was going to be in the wrong order and we'd have to switch it, but it doesn't matter. So there you go. By adding and subtracting just a form of 0 here, we were able to prove the product rule. So quotient rule, similar idea. Give it a shot if you want to. Very similar proof. Love you guys. That's why I'm here. Have an excellent day.